This is a video for OCR Pure Core Mathematics, second order differential equations 2, non-homogeneous equations, 2.5, particular integrals, exponential functions. If you've seen the previous videos in this sequence, you will have seen this slide before. It's just a reminder that we get the complementary function from the homogeneous version of the equation. We find the particular integral by using a trial function that's of the same type as this function on the right hand side, fx, and then we form the general solution by adding together the complementary function and the particular integral. Let's have a look at this example. We know what the complementary function is, so we're really only interested in the particular integral in this case, and for that I'm going to try y is equal to a e to the minus 2x. If I differentiate that, I'm going to get that dy by dx is equal to minus 2a e to the minus 2x, and the second derivative d2y by dx squared is equal to 4a e to the minus 2x. And again, we're going to plug these into the differential equation as we've got it up there. So we're going to get 4a e to the minus 2x minus, well, it's minus 2a e to the minus 2x, so I'm going to get plus 2a e to the minus 2x. And then it's minus 2y, so I'm going to get minus 2a e to the minus 2x. And that's got to be equal to 3 e to the minus 2x. Well, pulling those together, I've got 4a plus 2a minus 2a, so I've got 4a is equal to 3, and therefore a is equal to 3/4. So my particular integral is going to be y is equal to 3/4 of e to the minus 2x. There's that working tidied up for you. There's the particular integral a to the minus 2x with its derivatives plugged into the equation to give me a value for a of 3/4. And actually I've got it listed here as a decimal, so y is equal to 0.75 e to the minus 2x. So if we want the general solution to this differential equation, we know the complementary function. This differential equation we've done a number of times now. That's the complementary function, and there's the particular integral, and of course the general solution is the complementary function plus the particular integral. So we're going to have a look at a dynamic plot of this curve, and in fact I've got each of the three parts plotted on here. So the yellow line is the 0.75 e to the minus 2x. The green line is the 0.6 e to the minus x, and the blue line is the minus 0.05 e to the 2x. That's using these parameters for a and b. And as I alter these parameters, both the dotted lines and the overall solution curve will change accordingly. Notice that this curve is really being driven by the e to the 2x and e to the minus 2x bits. E to the 2x and e to the minus 2x are considerably larger as x gets larger. They are considerably larger than the e to the minus x bit of the function. So up here on the left hand side, the e to the minus 2x is doing all the hard work, and on the right hand side it's the e to the 2x. Now I've got a negative value for a, which means that my e to the 2x is actually mirrored. It's flipped over and pointing downwards. If I bring a up to be positive, you'll see that I've got a more recognizable e to the 2x type curve, and the red curve is tracking that very closely. If I change the value of b, actually not a lot happens to the solution curve. It does have an effect, but you can see as we bring b down smaller and smaller, it actually has an even smaller effect on the whole thing, and it really is being driven by e to the minus 2x. What happens at 0 values? Well, if b is 0, we're just being driven by e to the 2x and e to the minus 2x bits of the function, and so it just sits between those two. If a is 0, then it's basically being driven by the e to the minus 2x. Although e to the minus x does have an effect, it's not as significant as the effect of the e to the minus 2x. So here's our collection building up for the types of trial function we would use for different functions on the right-hand side of our differential equation. For linear functions and polynomial functions, we've seen those already now, and we've seen trig functions, and now we can add exponential functions to our list where we use functions of the form ae to the px. The next and final video in this sequence is 2.6, Particular Integrals, Special Cases.